greetings. Welcome to the unit 2 of this course on select or special topics in classical mechanics, and this unit will be on oscillators. We will learn a little bit about resonances and also a little bit about the wave phenomena. Now, an oscillation is basically, in its simplest form, any repetitive physical phenomenon. So, it could be just the swaying of the leaves, when a gentle breeze goes past these leaves, on these leaves sort of they start swaying and it moves a little bit and then crosses an equilibrium point, gets back. So, it could be easily set into what we call as an oscillation. So, it is any repetitive phenomenon. We see it all the time around us in nature. In the water waves, for example, if you look at the surface of a water and then you see that the level pops up and down a little bit, and then you also have this popping of the waves which travels along the surface, and you could have water waves. So, the oscillations, the phenomenon of the oscillations and the wave phenomenon, they really go together. Now, this is a very common phenomenon, and it you see it in the pendulum, for example. Then the light around us consists of electromagnetic waves, and the electric vector and the magnetic vector which constitutes the electromagnetic waves, they perform certain oscillations about equilibrium points. Then there are biorhythms, and then even things like share markets which fluctuate, and I will not be talking very much about it because never had enough money to invest in that. But then in other physical phenomena like molecular vibrations in atomic physics and molecular physics and solid state physics and so on, oscillations do find themselves play an important role in just about every physical process in a very big way. So, it is very important to learn oscillations from the fundamental principles. Now, here you see a famous experiment which is known as the Young's double slit experiment, and you have got light passing through one slit over here, and then the subsequent passage is through two slits, one over here and one over here. This is described often as one of the most beautiful experiments in physics, and then what you see on a screen is a fringe pattern, alternate occurrences of dark and bright fringes. Now, to explain this, you need what is called as a wave theory of light, and this also has for its first principles, one would begin analyzing this from the notion of oscillators. Then in musical instruments or music of any kind, vocal music, music coming from instruments, percussion instruments or whatever, unfortunately this is true also for the noise, not just for music, but then the basic phenomenology is based on oscillations. Light properties are described in terms of oscillations, and this is the picture of a traffic policeman who is using a speed gun, and what he is doing is monitoring the speed of oncoming traffic to check if they are traveling at at the speed limits or lower than speed limits. He is always delighted when they are driving faster so that he can charge them. But this also again is based on the principles of oscillations. And then there are quantum phenomena. In quantum mechanics, you have the phenomenon of quantum oscillators, and these are again almost ubiquitous in quantum mechanics. And here is a picture of a nuclear magnetic resonance imaging technique which is used to map the body tomography, and this is done again using the principles of oscillations, and the basic physics in in electronic oscillators and so on is what we are going to discuss in this unit. Here is a picture of Fourier, if you have recognized, and he is one person who contributed very rich knowledge to this field. What are our learning goals for this unit? We will first of all begin by recognizing what is a stable equilibrium, what is unstable equilibrium, and what is neutral equilibrium. We will also understand what are meant by saddle points. We will learn that if you go close enough to any point of stable equilibrium, motion can always be described by the simple harmonic oscillator. And this is really amazing, because this will tell you why the physics of oscillations is so important, because close enough, of course one has to define what is meant by close enough, and I will discuss it as we go along this discussion. If you go close enough to a point of stable equilibrium, motion can always be described in terms of a simple harmonic oscillator. Then we will discover that the same physics governs a lot of phenomena, means so it enables us develop analogues between mechanical systems, electrical systems. So there are these famous electromechanical analogues, and then we will go on to learn the effects of damping, because damping is something which is very real. You often develop the physics for ideal systems in which there is no damping, but then you have to deal with damping in the real physical systems, and then we will figure out how to work with damping, and then we will also learn how to deal with these oscillators when their dynamics is governed not just by damping, but also by an external driving force. So, these are some of the things that we will learn in this unit. We will then introduce ourselves to the phenomenon of resonances in physical systems, and then we will study about measurement techniques and what is known as the quality factor, and these are intimately connected with the physics of resonances. And then we will also learn a little bit about wave motion, which has important consequences both in classical mechanics as well as quantum theory. Now, in unit 1 we dealt with classical mechanics, and the governing principle that we employed in unit 1 was the Newtonian formulation of classical mechanics, and which is based on this linear response theory, that you have got a target and how this target responds to a stimulus, and when the response is linearly proportional to the stimulus, you have the equation of motion, namely the Newton's equation of motion, F equal to ma as we call it, and it is based on this cause effect relationship, and we could analyze the evolution of a mechanical system by solving this equation of motion. We also learned that the mechanical evolution of a system, of a classical system, can also be described by using an alternative principle, not just the principle of causality, but also the principle of variation, in which is based on the Hamilton's principle of extremum action, and this leads to alternative differential equations, either the Lagrange's differential equation or the Hamilton's equations, and these can also be used to solve the equation of motion and observe the evolution of the mechanical system over a passage of time. Given initial conditions, you can track the development of the mechanical system. So, this is how problems are solved in mechanics, and we have also learned that both of these techniques, whether based on the Newtonian principle of linear response and the principle of causality, or on the principle of variation of Hamilton, you get essentially the same results. Now, the object of this course is really not so much to develop a handle on Hamilton's principle or the Lagrange's equations of motion. We introduce that to provide an alternative way of following a system evolution, but this course is not about Lagrangian mechanics or Hamiltonian mechanics, because that is a very specialized area, and students usually are exposed to this at a somewhat later stage of education in college. So, at this level at which this course is really structured, it is only the concepts, only the essential concepts of the Hamiltonian principle which were of importance, so that you understand the alternative development of classical mechanics and also develop some insight in the connections between symmetry and conservation laws, which come out so nicely in a Hamiltonian and Lagrangian formulation. So, what we are going to do now is to focus on the Newtonian methods. They give us equally powerful a tool to analyze the mechanical evolution of a system, and the basic idea in this is to solve the equation of motion, which is F equal to ma, and then given the initial conditions for position and velocity, one can always track the evolution of the mechanical system. So, this is our basic tool, which is the Newtonian mechanics and the Newton's laws of motion, and we will now discuss the dynamics of systems when they are either in a state of equilibrium, in which case they will remain in the state of equilibrium forever. If it happens to be in a state of equilibrium, if there is no external force which is acting on it, then it will remain in the state of equilibrium forever, which is essentially Galileo's law of inertia or Newton's first law. If it is not in a state of equilibrium, then of course the system will respond and it will get accelerated by the stimulus, because the departure from equilibrium is indicated by the presence of an interaction which is a stimulus, which will cause the system to respond and in a manner so that the response is directly linearly proportional to the stimulus. So, when we talk about equilibrium, there are different kinds of equilibrium that you talk about, and this is a simple one dimensional potential, and it is flat over here, then it goes through a valley, then a hump, and then another valley, and then another hump, and so on. And as we know, when it is at the bottom of any of these valleys, then the system is in a state of equilibrium, just the way you see this cone placed nicely comfortably in this state, and you know that it is going to stay there forever and it is very stable. Likewise, if it is at the top of this hump, it is again in a state of equilibrium, and it would be like a inverted cone. The reason is that any slight departure from this would tend to push this system away from that point, whereas if it is close to a stable equilibrium, if it is pushed slightly away one way or another, it will tend to recover and come back to the state of equilibrium. So, this is the difference between a stable equilibrium and an unstable equilibrium. On the other hand, if it is in a region where the potential is flat, then it is a state of what is called as a neutral equilibrium. So, these are the different kinds of equilibria in one dimensional systems, and then let us ask a question that if you have two positive charges and you keep a test charge, a positive test charge right in the middle, let us ask this question: is it in a state of equilibrium? Now, you have two exactly equal positive charges and a test charge is kept exactly in the middle, and the question is it in a state of equilibrium? Now, obviously yes, it is in a state of equilibrium, and now we ask the question, is it in a state of unstable equilibrium or is it in a state of stable equilibrium? So, that really depends on what kind of displacement we are talking about. So, if you displace it along this line, which is the transverse line between these two charges, then the charges along the horizontal line will cancel each other. The forces due to these two charges along the horizontal line will cancel each other, and the one along the vertical line will tend to push this charge further and further away from the original point, making it a point of unstable equilibrium, because any slight displacement along the transverse direction will push the charge further away, and it will end up going to infinity, either to the top or to the bottom in whichever direction it is displaced first. So, that is the direction of displacement, in which case this is like unstable equilibrium. On the other hand, if the charge meets a marginal displacement along the longitudinal axis, along the axis which connects the two charges, then if it is moved to the left, then the force due to this will become stronger, which will push it back to the equilibrium, and as it does so, it will go past this, gain a certain amount of kinetic energy, and it could go past this, and then it will find itself on this side, and then this charge will push it back. So, this kind of displacement will tend to bring the charge back to its original point all the time. So, that will make it a point of stable equilibrium. So, the original point itself is certainly an equilibrium, but then whether it is an unstable equilibrium or stable equilibrium depends on the direction in which the test charge is dislodged. So, such a point is called as a saddle point, because this is the picture of a saddle, and you can see that if you place a marble at this center, which is a point of equilibrium, it will sit comfortably over there. But if the marble receives a little bit of displacement along the transverse direction, which is along the width of the horse, then the marble would fly away, it would go away from the equilibrium point, and that will be an unstable equilibrium. On the other hand, if the marble is displaced along the length of the horse like this, then it will tend to come back to the original point. So, this is the picture of a saddle point, and an equilibrium of this kind, which is stable with reference to displacement in one direction, but unstable with reference to another direction, is what is called as a saddle point. So, these are the different kinds of equilibria that one talks about: stable equilibrium, unstable equilibrium, neutral equilibrium, and also a saddle point. Now, we are going to deal with small oscillations, and the term small oscillations has a very characteristic significance in our discussion. So, we need to understand what is meant by small. Means is it this, if an oscillation is restricted to this range, is it small, or is it restricted to this range, is it small, or is it restricted to this range? How small is small? And this is the question that we need to talk about, because the smallness and the largeness is with reference to some other size parameter, and we need to understand the size parameter. So, if you have a potential of this kind, and you see that I have plotted a one dimensional potential, it has got humps and valleys. So, it has got positions of stable equilibria, unstable equilibria, but notice that the shape of the stable equilibrium over here is similar to the shape of the stable equilibrium over here, but but it is not exactly the same. Okay. This valley is a little bit narrower than this valley in a certain sense, and this is a qualitative description. We need to quantify this. Okay. We have to develop a quantitative estimate of this, because the shape is certainly similar, but not exactly the same. There are differences. So, what we will do is to expand this potential about the point of stable equilibrium, and one can if the function is analytical, if the function is continuous, it possesses continuous derivatives, then you can have an infinite power series, so that the function at a neighboring point x will be equal to the value of the function at the equilibrium point x0 plus the difference x minus x0 multiplied by the derivative of the function evaluated at the point x0. So, this will give you the first order correction, but then you really have an infinite series, and the subsequent term will be quadratic in this displacement. It will contain the second order derivative and scaled by this factor of 1 over root 2. So, you are all familiar with this infinite power series expansion, and this is the kind of power series expansion that we will use to describe the potential at a point x in the vicinity of an equilibrium. Now, near the equilibrium, notice that the tangent to this u becomes parallel to the x axis. which means that this derivative goes to 0, and if this derivative goes to 0, then this term, which is the first order correction to this potential, vanishes. And now this term having vanished, the potential at a neighboring point near the equilibrium is then given by the value of the potential at the equilibrium point plus this second order term and the third order term, and so on. Now the next term will be x minus x 0 to the power 4, the one after that will be x minus x 0 to the power 5, and so on. So the powers of x minus x 0 are increasing in successive terms, and if x minus x 0 is small, then its square is smaller still, the cube is even more smaller, the fourth power will be even more smaller, and this series will converge very rapidly. And depending on the level of approximation you want to make, you can always find a region which is close enough to the equilibrium point, so that you can retain only this term in your approximation and ignore all successive powers of x minus x 0. So if you go sufficiently close to the equilibrium point, and this is the meaning of what is called as sufficiently close. Sufficiently close means a region which is close enough where you can ignore the cube, but not the second power of x minus x 0, and that depends on the accuracy with which you want to measure these things. So if you go sufficiently close to x minus x 0, then you can always throw off these higher order terms, and this is essentially an approximation, this is not exact, and if you ignore these higher order terms, then close enough to the equilibrium point you have got the first term, this term strikes itself off because del u by del x is 0, and then you have got this quadratic term, and if you presume that u x 0 is equal to 0, this is just choosing a gauge for the potential, that you measure the potential on a scale such that this potential is equal to 0, and then if you choose the origin of the x axis so that x 0 is equal to 0, then this relation is nothing but u x nearly equal to half k x square, and if you plot it, if you plot u as a function of x, you essentially get a parabolic quadratic potential. So this is the famous quadratic potential for a linear harmonic oscillator, because the restoring force, if you develop if you cause a displacement of an object in equilibrium which is at the bottom of this valley and you push it sideways, then it will no longer remain in a state of equilibrium and it will experience a force, and that force is given by the negative gradient of the potential, right. So minus du by dx will be the force which will act on it, and if this force is proportional to the displacement, and because this is a force which is always directed to the equilibrium, if you push it to the left, the force will be directed to the right, if you push it to the right, it will be directed to the left, which is why it is called as a restoring force, and the restoring force is always proportional to the displacement, and this gives you the equation of motion for a linear harmonic oscillator. Now why this is an oscillator will be known once we solve this differential equation and look at the solution, because the solution will turn out to be oscillatory. Okay. So this is the differential equation for what is called as the linear harmonic oscillator, and this is, I have considered the case of an object which is in a parabolic potential given by half k x square. Now yes.
Harmonic oscillator only an approximation, or in real sense is it an anharmonic?
Well, this is an approximation to the potential. The actual potential can always be anharmonic, even in the case that I considered. Okay, in this potential which we have plotted, okay, we are not pretending that the potential over here is strictly harmonic. What we are saying is that if you go close enough to the equilibrium point where you can throw off the cube, and that is a pretense, that pretense is what the approximation is about. Whenever you are talking about an approximation, you are saying that a certain quantity is nearly equal to the other side of an equation. It is not exactly equal. When you say 2 into 2 is equal to 4, you have an exact equality, but when you say that 2 into 1.9 is nearly equal to 4, you are dealing with an approximation. So here the left hand side gives you the exact potential at the point x, the right hand side is an infinite series. If you consider all the infinite series, you have an exact, you have an equality. But if you say that x minus x 0 is small enough that I can ignore higher order terms. So in real potentials, these higher order terms will always be present, because the potential does require this infinite power series to be used. So it is an approximation, and it is a good enough approximation in a large number of physical situations, which is why it is so powerful. Now the reason it is useful in such a large number of situations is because in every situation you can always go close enough to the equilibrium point, and if you go sufficiently close either over here or over here, you can always find a region where you can find that you are comfortable ignoring this term compared to the quadratic term. If you go close enough, then you have a quadratic approximation. That is what your approximate linear harmonic oscillator, otherwise anharmonicity is always present. So this kind of situation happens for a mass spring oscillator, for example, that if you have a mass suspended with a spring and you push it a little bit and then let go, and then the spring has got a restoring force because it has got elastic properties. So there is a tendency of the material to recover from the strain, and then it tries to come back to its original configuration. So it will come back and then overshoot the position of equilibrium, and then because it would have acquired a little bit of kinetic energy, and then there will be these continuous transformations between kinetic energy and potential energy, and the mass will be set into oscillations. So this will be a periodic kind of behavior, and this will constitute an oscillator. Now this oscillator will go through one cycle at a certain rate, and it will go through a certain number of oscillations in a given unit of time. So that is your frequency nu, and twice pi nu is what is called a circular frequency. Why it is called a circular frequency will also become clear as we discuss it in the next few minutes, but the reason it is called as a circular frequency is because of its connection with what is called as uniform circular motion, because the equation of motion which governs this is the same that would govern the motion of the shadow of an object which is in circular motion. So if you have this red piece of ball which is in uniform circular motion in this vertical plane, and you have got light shining on it from the top, and if you look at the shadow of this red circle which is falling over here, then as this red ball is going along this arc, this shadow will be moving from right to the left, and when it comes over here, by the time it goes to the extreme point over here and then it continues its motion over here, the shadow will move back and start moving from left to the right. So the shadow will exercise an oscillatory motion. So there is a connection between circular motion and a periodic motion, so which is why the corresponding frequency is called as circular frequency, and this actually the shadow itself will constitute a simple harmonic motion. Now this is called as a reference circle for simple harmonic oscillations. Now this kind of phenomenon takes place in completely different kinds of systems. So, we now are talking about a mechanical system. Suppose you just have a electrical circuit which is made up of an inductance L and a capacitor C, and let us say you have a charged capacitor and then you connect it up and let go. Now, what is going to happen is that the current and voltage in the conductance in the inductance L and in the capacitor, they do not go to the peak together. Now, that kind of thing happens only in resistive circuits, but if you have non-resistive components, if you have an inductive component, an inductance, or if you have a capacitance, then the current and the voltage do not go in the same step. What happens is that the current is actually proportional to dV by dt rather than to the voltage. When it is proportional to the voltage itself, you have an ohmic circuit. So, that is the dynamics is governed by the Ohm's law, that is a resistive circuit, but in a circuit in which you have got an inductance and a capacitance, then the current is proportional to the rate of change of the voltage rather than the voltage itself. So, in such circuits what happens is that the voltage and the current do not peak together. The voltage actually lags the current in a capacitor by 90 degrees, and in an inductance it leads the current. So, how would you show it in a diagram? If you pick a direction for the current, then the voltage lags the current in the capacitor by 90 degrees. So, that is shown by this arrow over here, and it leads the current by 90 degrees as it is shown by this arrow over here. So, this diagram which keeps track of the phase, this is called as a phasor diagram, and we find that these systems, system of this kind, it is an electrical system, but it is described by essentially the same kind of equation as is involved in the description of a mass spring simple harmonic oscillator. So, let us see how this equation of motion is set up. So, you have got the voltage across the capacitance, which is given by this ratio of charge over capacitance. The voltage across the inductance is given by the this comes from the Faraday lens kind of consideration, and you have the L di by dt factor, and the current itself is dq by dt. So, you get the second time derivative of the charge, and the second time derivative is indicated by these two dots. So, the dot in our notation, let me remind you, as we did in the unit 1 as well, represents the derivative with respect to time, and two dots represent the second order derivative with respect to time. So, now it is very simple, because we have got the current, which is the rate of change of charge, how it flows, how the charge flows. So, it will be given by dq by dt. Q itself is CV. So, this goes as dc times dV by dt. So, because the capacitance C is a constant, and we see that the current is actually proportional to dV by dt. This is the point I was making earlier, that in a resistive circuit the current is directly proportional to the potential V, like in ohmic circuits and purely resistive circuits, but not so in LC circuits. So, now if you just set up this basic relationship minus VL plus VC equal to 0, as it will have to be, and then you just substitute these two quantities, you get an equation of motion for the charge. The second time derivative of the charge is directly proportional to the charge. This is the proportionality 1 over LC, and there is a minus sign. Now, you will immediately recognize that this is very similar to the equation of motion for a simple harmonic oscillator. So, in fact, as you see, if you have a simple pendulum which is stretched out to its one extreme position and you let go, this is the same kind of situation as that of a mass spring oscillator, and we consider those cases in which we presume that this is riding on a frictionless surface. Just like this pendulum, we believe that it is, in the first approximation we do not deal with damping. So, we will presume that it is not meeting any resistance of the air medium, nor at the point of fulcrum, at the point of support or anywhere. then this situation is very similar to that in an LC circuit, in which you have got the capacitance charged to the maximum, there is no current, you just connect the whole circuit, and with reference to the shadow of this ball which is going on in uniform circular motion, and we see the shadow of this ball in the light which is falling from the top, and then this is the shadow, then this shadow will start moving from this end to the left. If you look at it just a moment later, then this angle would have decreased, this mass would have moved further here, the current would have started flowing over here, and this shadow will be in a state of motion toward the equilibrium point. And if you see it few moments later, you will see that you can actually find the exact one-to-one correspondence between the motion of this pendulum or the mass spring oscillator or the LC circuit or the uniform circular motion and its shadow, and they all describe essentially the same phenomenology. At the extreme position on the left, when this pendulum has come all the way to its leftmost orientation, and then that the current will come to a 0, and then it will start flowing backward, and this will set the whole system, whatever the system is, whether it is a pendulum or a mass spring oscillator or an LC circuit or the shadow, what you are going to see is an oscillator. So these are the electromechanical analogues, and you see it in the equation of motion, that in the mass spring oscillator the equation of motion is given by the acceleration given by minus k over m times x, and in the LC circuit the second derivative of the charge, this is the second derivative of position, second time derivative of position, this is the second time derivative of charge, and these are proportional to the corresponding quantities x over here, q over here, and then if you look at the proportionalities, which is k over m and 1 over LC over here, both having the same minus sign over here, then you can immediately see a correspondence between the quantities k, m and LC. So you see that the inductance plays the same role in electric circuits as mass or inertia does in mechanical systems, and the capacitance plays the same role as the inverse spring constant, which is sometimes called as a compliance. So this is the general equation of motion. Now we will not worry about calling it as x for position displacement or charge for the corresponding analog in the electrical circuits. We will write this for some degree of freedom, which is q. So q is our typical prototype of the displacement. It could be a position displacement, it could be angle, no matter what, and the equation of motion that we are looking at is that the second time derivative of q is proportional to the q itself. It is always directed to the word q equal to 0, so there is a minus sign, there is a proportionality alpha, this is a second order differential equation. Its most general solution will contain two unknown constants a and b, which will have to be determined, and this is the most general solution, and this, if you just put this solution in the differential equation, then it is a matter of simple algebra to find that this omega 0 is nothing but the square root of alpha. So a and b are to be determined, and these will be determined by the initial conditions, and you need two initial conditions for this. One is what is the value of q at t equal to 0, and what is the value of q dot at t equal to 0. So these are the initial position and initial velocity for a mechanical system. So we can immediately see that if you use this general differential equation for an arbitrary degree of freedom q, then whether it is a mechanical system or an electrical circuit, you can get the solutions by solving the same differential equation, and you do not have to do this physics again and again for different systems. So you just set up one equation of motion, and then it will be applicable to every situation where you can use the quadratic potential approximation. Now I will leave you with this question: if we could have associated L with 1 over k and C with m, but I will let you worry about it. So, this is the differential equation for the charge, and Feynman in fact calls this in his famous lectures as Newton's law of electricity. Means of course, Newton's law of motion was meant for mechanical systems. At the time of Newton, electrical circuits did not exist, and Newton did not constitute this for any law, any electrical circuit, but this equation of motion is what Feynman calls as Newton's law of electricity, and obviously for the reason that you have two initial conditions which provide the solutions for the equation of motion, and essentially in the same formalism in which Newtonian mechanics is developed in the linear response formalism, because it is the same kind of situation which governs the dynamics. So, this is our story here. We have to determine A and B by initial conditions. The frequency nu, or twice pi nu, which is omega 0, is determined by whatever this proportionality is between acceleration and the position, and this is what determines the frequency. So, at time t equal to 0, if you put t equal to 0, e to the power 0 will give you 1, same here, and q at t equal to 0 will give you a plus b, right. So, q at t equal to 0 is a plus b, and q dot will give you I omega 0 times a minus b, because the exponential function is the easiest one to differentiate. It is the derivative of e to the I x, or e to the x is the same as e to the x, and then you can take subsequent derivatives. So, this is a very easy function to deal with in elementary calculus. So, you can then determine A and B. You have got two equations for these two unknowns A and B. One is this: q at t equal to 0 must be the sum of A and B, and the difference of A and B multiplied by I omega 0 is equal to the initial velocity. So, from the initial position and the initial velocity, you can get the values of A and B, and that really sets up the problem for you. And once you have it, you can predict what q will be at any time t, and your problem is solved, because that is exactly what the mechanical problem is about. That if you can trace the evolution of the mechanical system and predict what the position will be at a later time, or what the velocity will be at a later time, given what the initial position and velocity is, then you have solved the mechanical problem. So, that is a complete solution. Now, what happens in a ideal oscillator, and I am presuming that this is an ideal oscillator, in which, by which I mean that I am having faith in the approximation we have made. We are pretending that the other terms which we have ignored, the anharmonic terms that we talked about a little while ago, they are of no importance, and if it is an ideal system in which this quadratic potential approximation gives us the true mechanical evolution of the system, then the average kinetic energy. What is meant by average? Average is, you can see that the kinetic energy at different points of the oscillation will not be the same, but if you take the average, if you add up the kinetic energy at every instant of time over the entire cycle, then you get, and divided by the total time period for that cycle, then you get the average kinetic energy, and it is this average which I am talking about, and it is indicated by writing kinetic energy in these angular brackets. So, this angular bracket is my notation to represent the mean kinetic energy or the average kinetic energy. Likewise, we have the mean potential energy, which is the average of this half kx square, and the average will then be determined by taking this time integral of any function over one period and dividing it by the total time period itself. That is how you will determine average, and when you have to determine the average kinetic energy, you will need the average of x dot square, and x dot will come from the time derivative of this. So, you will get from the derivative of the sine function, you will get the cosine function, and you will need a cosine square, whereas when you take the average of the potential energy, you will need to take the average of x square, which will the average of the sine square function. So, in one case you need the average of the sine square function, and in the other you need the average of the cos square function, and over the entire angle of 2 pi this average is exactly equal to half for both the sine square as well as the cosine square. So, this enables us to determine what is the average kinetic energy by taking half m times the average of x dot square, and this will turn out to be, this is elementary algebra, I will let you work out the details. So, this is 1/4 a square m omega 0 square. The reason is this ratio k over m is the square of omega 0. So, as a result of that you get 1/4 a square m omega 0 square, and the average of potential energy also has got a factor of 1/4 a square, and here you have got k, but these two are exactly equal to each other because omega 0 square is nothing but k over m. So, the average kinetic energy and the average potential energy are exactly equal. Now, this is quite appropriate for an ideal oscillator. Now, I will suggest some exercises over here. We have already discussed this electrical circuit, we have already got the general solution, and I suggest that you actually plot on a piece of graph paper the position and velocity as functions of time, also plot instantaneous voltage and instantaneous current as function of time, find out what is the phase difference between position and velocity, and likewise what is the phase difference between current and voltage. So, these are nice graphs to be plotted, and it will help you develop some insight into the physics of these systems. Now, we will talk about coupled oscillators, because one of the very fundamental principles in physics which holds in a large number of physical phenomena, not that it holds in every case, but the principle of superposition is a very strong principle in physics, and a large number of physical systems are governed by the principle of superposition, and we will now discuss it in the context of coupled oscillators. Like if you have two oscillators and they are coupled, then what will be the net motion? So, this will be described by the superposition of two oscillators, and there are some very nice examples which I have drawn from Berkeley's physics course. The volume 1 is on mechanics, and there are simple examples of this kind, that you have got a mass which is attached to two springs, one on this side and one on the other, or two springs which are held together. They have this kind of a configuration as shown in this, and these are they can carry out oscillations on a frictionless support. And in both these pictures there is one thing which is common, that if you displace this to the left, this spring 1 will push this mass back to the right, and spring 2 will also pull it toward the right. So, the forces of the two springs will be in the same direction, although in one case it is push and the other case it is pull, but it will be in the same direction, and it is also the same in this configuration. So, the effect of the two springs will be supportive of each other. So, if they are springs of the same spring constant, you can easily determine what the effective spring constant of this combination of the springs will be like, because you know that they are acting similarly, they are acting in the same direction, they are supporting each other. So, they will enhance each other's elastic properties. Now, what happens if you provide it with a translational with a transverse displacement? So, if you have a relaxed length of a spring which is a0, and if the instantaneous stretch length is a, then the stretch is through this difference a minus a0. So, the tension will be proportional to the stretch, and the proportionality will be the spring constant. So, that is the tension, and if you have a displacement in the transverse direction, then this stretch will then sort of induce this object to be brought back toward the equilibrium, and the total restoring force will be minus 2t sin theta, because it is a component of this tension along this direction which will come in. So, that will be there will be a sin theta factor, and sin theta, as you can see from this figure, is nothing but the ratio x over L. So, you have 2 k L minus a 0 x over L. So, this is the kind of transverse oscillation that you can expect when you have a mass which is sandwiched between two springs, but set into oscillations not along the length of the springs, but along the transverse direction. So, this is again an example of two springs acting together. Now, again we have already talked about small oscillations, and I mentioned that you need to go close enough to the equilibrium point, and this is what develops the notion of small oscillations, and this generates in our minds a feeling that the small oscillations, because intuitively we have some idea of what a small oscillation is. So, if I say that okay, an oscillation is like this, you will agree that it is small, but if I say that an oscillation is like this, you might tend to worry that okay, I am no longer talking about small oscillations, right. Now, one has to understand that all this has at the back of the analysis a certain approximation scheme, and the smallness is always in the context of that approximation scheme. And I am going to show you an example of what is called as a slinky, that you have these transverse oscillations, and we have already written this equation of motion for the acceleration of an object, and here minus 2t sin theta, we have written t is k L minus a 0, sin theta is x over L, and now we can develop an approximation which is known as the Slinky approximation. Now, this approximation can be made when a 0 is much less than L, okay, because what happens when a 0 is much less than L, a 0 over L, this ratio becomes much less than 1, and this factor which is L minus a 0 over L, this factor becomes nearly equal to 1. So, you can actually cancel L minus a 0 over L. This numerator L minus a 0 becomes nearly equal to L in this approximation, and the resultant approximation is this x double dot. So, if you take m to the other side of the equation, it will come in the denominator. So, this will become minus 2 k over m times x in the approximation that L minus a 0 over L is nearly equal to 1. Now, this is obviously not exact, nevertheless it is a good approximation provided a 0 is much less than L. What are we talking about? If the relaxed length of the spring is much less than the instantaneous stretched length, okay, in that approximation you have an equation of motion which is exactly equal to that of a simple harmonic oscillator, that the acceleration is proportional to the displacement, it is dictated by this minus sign. So, it is always in the direction toward the equilibrium, and the proportionality which we call as the spring constant is scaled up by a factor of 2 in this case, right. So, this is what is called as a Slinky approximation, and in this approximation even if L itself is quite large, you can still have simple harmonic oscillations, and Siddharth is going to show us the Slinky. So, Siddharth, would you just come up, and then the cameras can be directed at this Slinky. Siddharth likes to play with this, and he has got what is called as a Slinky, and you can just hold it and show you, and he will show you how this works. So, this is a fairly large kind of oscillation, okay. So, this is not something that in the intuitive sense you will call as a small oscillation, okay. This is of course not what you might call as a small oscillation, but in the context in which we are discussing it, in the approximation which works out, thank you Siddharth, could you get the image? You got it, okay. So, in the context in which we are talking about, this is an excellent approximation, and this is called as the Slinky approximation, and for this slinky you have large values of L, and the slinky works as a simple harmonic oscillator over fairly large sized oscillations without losing what we call as a linear elasticity, something within the limits of the Hooke's law, if you might want to call it that way. And a typical slinky of A0, which is about 3 inches, I believe that is about the size of the slinky that you had, about 3 inches, right Siddharth, more or less. And then if you stretch it, it would go as much as 10 feet, maybe 12, 15 feet, and that is a typical slinky. And if you really stretch it without losing the linear elasticity, it can still exhibit simple harmonic oscillations. So this phenomenon is very widespread, and it describes a large number of situations, as you can see from this figure. You are governed, the dynamics is governed by the simple equation of motion, and we find that if q0 cosine omega t is a function which represents the solution to the differential equation, then if you phase shift the argument of the cosine function by an angle phi, which must be a constant, but constant with respect to what? Constant with respect to time. It can certainly depend on some other variable, so it can depend on x. So if you have a solution in which the argument of the cosine function is phase shifted through an angle which is independent of time, it must be independent of time, but it can depend on x, then this is also a solution of the same differential equation. So you can have solutions of different kinds, and they will all be phase shifted from each other, determined by the initial conditions, and we ask the general question, what should be the functional form of phi? What should be the dependence on x of the function phi? What can it be? Okay, because phi is some arbitrary function of x in the manner in which we have represented it over here. Now we are asking what should be the exact dependence on x of this function phi. Now what we do know is that over one wavelength phi must change by 2 pi. Okay. So the rate of change of phi with respect to x, which is d phi by dx, must be 2 pi by lambda. Okay, because over one wavelength the angle phi should change by 2 pi. So the rate of change must be equal to 2 pi by lambda. Now you have got a simple differential equation, just integrated, the solution is obvious, phi must be 2 pi by lambda times x plus some constant of integration which you cannot rule out. Okay. So this is the dependence of phi on x, phi must depend linearly on x. So phi is equal to kx plus delta is your solution, and you get the exact dependence on the argument x of phi. So here you are, you have phi equal to kx plus delta, and the total phase of the cosine function is this angle here, which has got a time parameter, it has got a space parameter. The time parameter is scaled by the circular frequency omega, and the space parameter is scaled by the spring constant k. Now this spring constant is some appropriate factor in your linear harmonic oscillator. So you have to invoke the electromechanical analogues if you are talking about the electrical circuit. So in the electrical circuit, k is not the spring constant, but you have already met the electromechanical analog. So you can replace mass by the inductance and the capacitance, or with the inverse spring constant by the compliance, right. So you have these oscillations, and if you have got an x axis with an origin over here, and then this is the phase of the cosine angle, and if this is in an extended medium, so you do not have just a point which is in oscillation, but you have got a whole medium, and in this medium, this entire medium is set into some kind of oscillations, and in this entire medium you ask what is the connection between oscillation at one point of the medium with that in another point of the medium. Are these oscillations in step with each other? Are they in step, or are they out of step? are they in phase or are they out of phase. Now, at some of the points in this medium they will be in step, and some of the points they will be out of step. So, you can ask, if you connect all the points in this medium at which the oscillation is in step, then you get a surface in the medium. It could be a flat surface, it could be a spherical surface, it could be a cylindrical surface, or it could be a warped surface, it could have any kind of shape. But a surface of constant phase will be described by all those points at which this theta is the same, this phase angle is the same, and if this angle is the same, it has got a certain value which is the constant for all the points on the surface, then for all the points on the surface, the angle theta being the same, the variation in this angle is 0. That is the equivalent statement of surface of a constant phase, because all the phase angles for all the points on the surface is essentially the same. So, there is no change in the phase angle from one point to the other point. So, this gives us the definition of a surface of constant phase. A surface of constant phase is then such a surface in the medium at which all the points are in a state of oscillation which are in step, in phase with each other, they are exactly in the same step, and they are described by the condition d theta is equal to 0. So, now theta is equal to this omega t plus or minus kx plus or minus delta, and if the differential in this is equal to 0, then the differential on the right hand side is equal to 0, of which omega is a constant, k is a constant, and delta is a constant. So, the differential in omega is 0, the only parameters which are changing on the right hand side are t and x. So, d theta equal to 0 gives us this relation omega dt plus or minus k dx equal to 0, because this arbitrary angle delta of course is a constant. So, omega dt plus or minus k dx is equal to 0, which essentially means that if you take dx by dt, it will be either minus or plus the ratio omega over k. Now, omega over k is an intrinsically positive constant quantity, right. Omega is the frequency, it is an intrinsically positive quantity, k is an intrinsically positive quantity, it is a spring constant. So, dx by dt can be either negative or positive, both the possibilities are open, and we therefore ask what is the nature of motion when dx by dt is negative and what is the nature of motion when dx by dt is positive. So, when dx by dt is negative, then x changes with time, but x decreases with time, because a decrease in x as time increases, this is the ratio of delta x over delta t. So, as delta t increases, as the denominator increases, if the numerator decreases, then the ratio will be negative, right. So, dx by dt will be negative, and this will obviously represent x decreasing with time, and the only way x could decrease as time increases if the surface of constant wave is moving from the right to the left, right. So, this is a wave which is travelling to the left. On the other hand, if dx by dt is positive, then x increases as time increases, and x increases as time increases if and only if the surface of constant phase moves from the left to the right. So, the dx by dt is what tells us the direction in which the surface of constant wave is travelling, and this is how you recognize whether a wave motion is travelling either to the left or to the right, and this is true for any function which is not just a cosine function, it could be some arbitrary function, and if the functional form is generally given by x minus vt, which is some description of a pulse, then if dx by dt is positive, then you have the pulse which is travelling to the right, and if you have a function where this sign is plus, then dx by dt will be less than 0 and you will have a pulse which is traveling to the left. So, a function x minus vt will be a pulse traveling to the right, whereas a function g x plus vt will be a pulse which travels to the left. Now, the traveling speed is automatically determined because a wave covers one wavelength in one periodic time. So, the ratio of this distance over time is what gives you the velocity, and this 1 over t is nothing but the frequency. So, v equal to nu lambda is a very famous relationship that you would have used. So, you can see the picture that if you have a motion of this kind and you have got one wavelength which is described between these 2 points, and if you take any point over here and see how this propagates in one direction, and then you have the corresponding propagation of wave. So, we will take a little break over here. If there are any question, I will be happy to answer, otherwise we will take a break and then we will be discussing how motion of this oscillator gets affected when damping is introduced.